So I will start with PyMAPDL, which is the Pythonic interface for MAPDL. So I was thinking how PyMAPDL can help you guys, people who use MAPDL in a normal day-to-day basis. So quick recap. What happens if I want to run a quick example? We include already the verification manual example, so you can run it very easily in 5 lines, or including all the imports. Basically in one line to read the file and another one for interactive plotting, as it shows on the right. You might want to check the loads that model has. It's very easy. You can get the nodes using mapdl.mesh.nodes, and then from there you will obtain the node as an array. You can play with it. You can use the ncel, which any MAPDL user will be familiar with. You can use mplot and plot the boundary condition as shows on the right. And on top of that, we provide some helpers, which in some functions, for example, in this case, or flist, which will convert the output instead of text as we are used to in MAPDL, we will get it as a data frame. Some other functions or methods will have the capability to export to lists or to NumPy arrays. So that's quite convenient and can help you a lot. You will avoid having to parse, which is normally a required task in any MAPDL, for any MAPDL developer. You might want to extract results easily. Well, you have several functions in the post-processing module. For example, you have the nodal displacement, where we are showing here the all. Basically, you are exporting in the X, Y, and Z coordinate the nodal displacement. You have other methods like nodal, like elemental displacement, like stresses, whatever you need is there. You might want to plot those results. It's very easy again. mapdl.postprocessing.plot nodal displacement, and you will have another interactive plot. This is a beam. Is a beam made of plane elements, so that's why it's flat. You might want to work with MAPDL array. If you are MAPDL user, working with exporting and importing arrays is always a bit complicated. And having to work with the start-get and the bget is a must, because they are both very important commands. But sometimes their usage is a bit complicated to interact with, and especially to be able to work with arrays in an easier way. So PyMAPDL provides some functions, for example, getValue, which expand or wraps the start-get, and the getArray, which wraps the vget. Okay, it's very easy, as you see, and you will obtain the values in your Python memory, let's say in the Python workspace as a NumPy arrays, and you can use them right away, like you will use in any Python NumPy array. You can also upload arrays from external files, which is very convenient. It can get a bit difficult to use command like tread or bread to get the data that you need in MAPDL. So this way you really simplify everything, and we provide it for you. You will just to load the array or the data using any Python tool, and then just save it as a parameter with the given name. So it's very convenient. You might want to work also with components. We are providing some helpers for defining the components and to explore what components have you defined. We allow you to interact through those elements in a very easy and convenient way, avoiding these kind of loops where you need to keep the number of elements that you in the component that you have, and you need to increment the index or using any ncel or nnext or something like that. So this is very convenient. And it's allowed, and also PyMAPDL allow us to reuse code using function or module. So you could reuse the same function for components several times and just change the component name that you want to analyze. So it's very convenient. You might want to run multiple MAPDL instances. For example, there might be cases that you want to run many examples or process many files, many RST files, or you want to process many variations of a geometry or process many different geometries. You can do that easily to coordinate MAPDL instances using MAPDL pool, where, as I mentioned before, a pool and a specific number of MAPDL instances will be launched, and you can manage them in a very convenient way. In this case, what I'm using this pool of 10 MAPDL instances is to read and execute the verification manual files, the 21 first verification manual files, and it's running on a batch. So you have 10 MAPDL pool, they run the first 10. Whenever one's finished one, it goes for the 11th, and so on until they finish the 21. So it's super convenient. We have also the possibility to convert your previous code. Imagine that you have some code that you have been working for a lot of time, or it has been in your company for years, and you want to reuse it. We provide the terminal, the command line capability to convert your file, your DAT or whatever file that you want with MAPDL code. We will convert it to equivalent PyMAPDL, to an equivalent PyMAPDL model that will take care of everything, including the imports, the launching of the model, etc. So it's super convenient. We have also included now we are working actually. This is work in progress for the HPC support. The idea is to launch and connect to remote instances running on an HPC, on a Slurm HPC cluster. We are looking for beta tester, so if you are interested, please contact me. We will be happy to talk with you and see your specific case. So let's go to the quick example. It's very quick. I didn't want to go too deep into details, but let's gonna show something that I think it could be very interesting for you guys, which is basically how to use PyMAPDL on a genetic algorithm. Some of the features that we are presenting in this problem is how to capture constraints using Python functions to represent complex conditions, the use of MAPDL pool, so you can run several iterations of several genes at the same time, and the coupling with a very well-known Python library from the Python ecosystem, which is PyGAD. It's conceptually is simple. You just need to define your model. Your model can have several functions. For example, one could be define the loads. In this case, define loads on your left will apply the boundary conditions in your model, and which that function will be coupled in a bigger function. We will define the material properties, the geometry, the finite elements. It will solve the model, and it will retrieve the data that you are interested in. For this case, we are doing something very simple. It's just a beam, a simple beam with some specific load, and we are trying to give for a given displacement. We are using genetic algorithm to kind of predict what was the load or the force applied. It's super simple, but it demonstrates that it can be done. Okay, so we need a fitness function that will be included in. It will be used for PyGAD for the optimization. In this function, we have the pool. The pool.next will basically returns the next available or free or MAPDL instance that is not being used. So every time that you run the fitness function, it will request to the pool, hey, give me a free MEPDL instance. And when it give it, you run the model that you want to. So it's very clear, the code. You calculate the error, you have the fitness criteria, which is basically the kind of error, fitness, etc. And then you iterate into that function many times. These are the results. This is just for kind of explain that, yeah, it works. I don't think it does makes much sense to explain the details of the model or anything. I just wanted to show that it works. It converges easily in about 100 genes at the 10th generation, which is pretty decent. But the most important part of here is that you can use PyMAPDL to couple with other Python libraries, and it should be a relatively process to do, and it should really empower your workflows, help you to do your work easier and faster and with more possibilities. And now very quickly to PyMechanical, quick advice, or let's say, did mention this on the previous meeting. When you want to start with PyMechanical, I would say one of the most and easiest way to do is that you start with a desktop app, because the API is very human friendly. I mean, you can kind of get around. It's easier to memorize that maybe, for example, PyMAPDL 4 letters or 6 letters command, but sometimes it's too verbose, you might get a bit lost. So until you get familiar with it, my advice is to use the recording feature in the Ansys Mechanical desktop. So you will obtain the code that you want, and then you can use that code in your preferred IDE to edit, parameterize, customize the code, and get the code tailored to your needs, basically. Once you are more familiar, you can start to use the autocomplete to navigate the tree on the different Python objects. Using global update globals in your script will give you access to mechanical globals such as model X API, which are used and needed in order to interact with the mechanical data model. And since 24R2, we have improved interactive plotting capabilities, which are very nice. You have some examples in the documentation, interactive examples. I really recommend you to visit the website and check them out. And for a very quick example, I'm just gonna dive in the PyMechanical side. I believe that my colleague Roberto is gonna go through this also very quick, because we are just trying to present the libraries. You always can go to the website, in this case is on the bottom, the link for it, and then go deep in the model and go deep in how this example works. But basically, it's an example where 3 libraries are used: PyAnsys, Geometry, PyMechanical, and PyDPF. I'm just gonna talk about PyMechanical. The other ones, very briefly, will be covered by Roberto, who is the real author of this example. Well, on the right, the commands to launch MEPD, to launch mechanical, very simple. And then you read the geometry. You have the commands on the bottom where you can set the format, the preference, if you want to process the selections or not. And you need to specify there where the file is located. You read that and you get the geometry, and you can plot them interactively. Then you can just mesh it. Is in this case we haven't done we haven't really go through all the options for generate the mesh, but for adding the result we give a bit of explanation, like how to add the transient thermal analysis, the solution at temperature, where you want to get the temperature proof, etc. As I say, the code, the API is it's a bit verbose, but it make it very human friendly. It's easy to memorize. It's easy to work with. So it might look a bit scary at the beginning, but give it a chance because it can get very, very convenient and comfortable to code with it. And then you have analysis setup. Okay, how do I set up a steady or a transient analysis? Model dot add steady state thermal analysis or add transient thermal analysis. It's very easy how to retrieve all the name selections for all the bodies in a simple loop, for example, how to add convection loads, how to add the field coefficient, etc. How to add a steady solution. The API is, as I say, is very powerful. It kind of reflects everything that can be done through the graphical user interface. So if you have any issue or you don't know how to do something, if you can do it on the graphical user interface, you can do it in PyMechanical, which is very convenient. And that's it. The post processing of that model is shown on DPF, and I think Roberto will go in more details about that. And I think I'm done, David.
Thank you, Herman. Yeah, thank you, Herman. I think next one is Pierre with the multi-threading and multiple DPF servers performance comparison with PyMAPDL. So Pierre, you want to share your screen?
Yes, let me just set the proper definition to it, and I'll be here in just a second. Do you see my screen?
Yes.
Good. So this is going to be a short presentation, but on an example that I worked on with a user, who asked me that question. So, he wanted to understand, what he could do with DPF, and what he was running into was the need for computing volume average stresses. So what does that mean? For any node in the model, you find the elements that are attached to this node within a given volume. So you give a threshold volume, you find the elements attached, and within those elements for that node, you average the stresses by the volume. So you take all stresses from the surrounding elements and you divide by the volume. If you want to do that with MAPDL or PyMAPDL, what you would have to do is run sequentially over each node, do a bunch of ESLN, NSLE, so selecting nodes from elements and elements from nodes and stuff like that. And that's fairly sequential. And in the end, you will get equivalent stresses and do the average on the volume. Let's see what DPF does on that. And the idea was to look at not only DPF, in standard sequential mode, but also DPF in a way where I would want to use multiple DPF servers at the same time. Because, okay, I have this information, but I really need to run node by node. And it would be so much more efficient if I could run multiple nodes at once than just taking one. So let's take a look at the performance, and I'll tell you how I did that. So what you see on the left-hand side is a graph that shows the time to extract the volume. So just to extract which elements should I consider for one node. And I've made it on a number of nodes. So I had a small model like the one you have on the right-hand side here. And I took 1,000 nodes, 5,000 nodes, 10,000 nodes, and the full model, which has 140,000 nodes, which is not big, by the way. And what you see is the time to extract that information. So if I am in MAPDL, which is the yellow bars, you see that it's ramping up. So the more nodes I take, the longer it takes because it's all sequential. And unfortunately, for some reason, I was not able to get it on the full model. but the number would be much higher anyway. Now, if I take DPF, and the interesting value to look at is actually the one on the left-hand side, where I wrote DPF1 thread. That's one DPF server. And obviously, well, you're going to send all nodes to that same server, so that's all going to be sequential. So with DPF, just one server, the full operation on the 140,000 node took 2,800 seconds, which is roughly what, a little over 45 minutes, some close to that. So what I said was, okay, now let me start multiple DPF servers and multi-thread the distribution of nodes on those servers, because if I run those multi-servers, I need a way to send, operations node by node on each server. So then I tried with 4 and 6, which is the results you have here. And you see that for small number of nodes, whether you use 1, 4, or 6 doesn't make a big difference. Yet, if you take the full model, you see that with 4 threads, I was able to divide the time by about 3. And with 6 threads, well, with a little over a factor of 2. So why 6 and 4 didn't give the same number? Well, just because I have 6 processors on my machine, so probably I was hitting some limits of my machine. But on a bigger one, you could expect that number to get much higher. So in practice, how do you do that? Sorry, I need to mute a chat because I don't need to see my own chat here. Yep, sorry. So how did I do that? So I have operations here. So I have a base operation for each node. So what I do for each node, and you see here the DPF code to replace ESLN and SLE. So we use the scoping transpose function, which is very useful. So when you have nodes, scoping transpose will give you the corresponding elements. And when you have elements, scoping transpose will give you the corresponding nodes. Super useful function. So, and in the end, I just returned the small element volume. You see, I had a threshold volume that I was going to use. Now, I did specify, a server for my DPF operator. So now when you use an operator, there is this server argument that you can use, which will send to a specific DPF server the function you want to run. So in this case, I'm using those multiple servers. Now, how do I spread the work? Well, the first thing I did was obviously to create my own servers. So that's the code you don't see here. But then for all the nodes, so I was copying, or looping over all nodes, I call this threads here. So I'm using the multi-thread library, so the import threading library in Python. And for each node, I was going to send it, so ask for that function that I just showed before. For the node number I was looking for a given threshold volume, for the mesh I wanted to look at. And here you see the server argument goes in. And I was just looping over my server, threading, sending a bunch of nodes to each server individually. And in the end, I just gather back all of the volume regions that I wanted to look at. So that's really, very briefly shown how to use multiple DPF servers and multiple threads to spread the work. This is not necessarily useful when you work on a full mesh, like when you work on all nodes at the same time. But in this case, we had to loop over node by node, and that's why, multiple servers and multi-threading was useful. So real quick example, not as advanced as it looks. When you get into it, it's kind of easy to understand. It might look a little weird in the beginning, but when you get into it, you'll find that it's very useful. And I had a chance to use it on other occasions with about the same success. So this is really going to speed up your processes when you have to work again on like an individual node basis, and you need to send the same function over and over again rather than working sequentially. That's it. Thank you.